Let's start with this session on software architecture. This is Harvinder Jabbal from BITS Pilani. This is the second module on design and documenting the architecture. Today we'll take up designing and architecture. The first three of the listed topics have already been covered. Define architectural significant requirements, gathering ASR from requirement documents, business goals and stakeholders, capturing ASR in and utility tree for further refinement. Today we discuss architecture design strategy and attribute-driven design method. This chapter will talk about design strategy, attribute-driven design method, steps of ADD, and then we briefly summarize whatever we have done. Let's look at design strategy. The design strategy presents ideas that are key to architectural design method. The first idea is decomposition. You have an application, you have a project, decompose it. So you can separate out the job into individual modules and attend to them individually. Then you design to architecturally significant requirements, either the entire application or parts of it. The third idea is generate and test. Okay, we generate a solution, we think it will work, we test it. If it doesn't, we get back again, redesign. So these three ideas are central to design strategy: decomposition, ASR, generate and test. What is decomposition? Architecture determines quality requirements. We have understood one thing very clearly by now, that architecture is all about satisfying the quality requirements or the quality attribute requirements for a project. Important quality attributes are characteristics of the whole system. However, it is possible that you may designate certain modules to implement the quality attribute requirements. We must understand then, we start designing with the whole system, then we decompose into parts, we designate ASRs to be satisfied by parts. Those that have got satisfied at a higher level can be taken as satisfied and we don't need to work on them any further. Any part will inherit automatically a quality attribute requirement that has been satisfied for one of its parent groups. So if something has been taken care of while thinking of the system as a whole, it will automatically be taken care of by each part. Designing does not necessarily mean working in a green field. You don't work from scratch. There could be some components that are given to you. The client may have decided that these components have to be used. Some of these components may be a part of the application itself. Well, you have to sell so-and-so product, so you cannot come out with a solution to sell something else. So whatever is given as a given component has got to be accommodated by the architecture. These are constraints. These are not items where you decide whether to have this component or not. Well, that component is there, you might as well accept it. Second idea was designing to architecturally significant requirements. These are significant requirements that have to be satisfied with the design. If these architecturally significant requirements are not satisfied, the stakeholders are not going to be happy. These are the requirements that have been prioritized by the stakeholders. They have told you through the various methods that if you execute as per the ASRs, we will take the project as complete. That's what we are paying for. These are normally a small number. If they are not, it was our task in the last discussion to find out how we limit the numbers, understand people's priority, and work against those priorities. So naturally, since we are working against priorities, they become the most important. Now, you could be an experienced architect, you may be raw. If you are a raw architect, you start designing to the most important ASR first. Take care of it. Having satisfied it, then look at the next, because there is no point satisfying items which are lower in the priority and leaving out what is right on top. Gradually, you go down step by step and try to take care of all the ASRs. If some ASRs at the lower end are left out, these could be candidates for negotiation. They could be candidates for looking up as to what to do, but only after you have satisfied ASRs at the higher level. More experienced designers with a vast exposure to similar systems might look at a list of ASRs and straight away think of designs which will satisfy a good number of ASRs in one go. So depending on how you are, there's no hard and fast rule. If you are not experienced, you work one at a time. But if you can satisfy all ASRs with a single design, so be it. Now, what about other quality requirements which are not in the ASR? Obviously, if they're not in the ASR, they were not prioritized by the stakeholders. Well, we will try to adjust them. We'll try to adjust them as long as the ASRs continue to be satisfied. If satisfying an additional quality requirement interferes with satisfying the ASR, we will hand out the ASRs, the stakeholders command, the meetings, the minutes, which said that the ASRs were the most significant. When we find that we could not satisfy them, we get back to these additional requirements and we suggest that we weaken them. You modify the requirements, or we modify the system so that at least these additional requirements are partly met. They may not be met completely, but they may be partly met. So that could be negotiated. Let's see, these were the architecturally significant requirements. These are your additional requirements. We cannot meet them as per the specs you are now asking for. So let's dilute the goal and satisfy it. If the customer, the client, the stakeholders are still adamant that no, nothing doing, these additional requirements have got to be met, we tell them, let's go back, let's again have one of our workshops and let's sort it out. Let's change our definition of ASRs. Let us say that since you've become so adamant about it at this stage, this was probably an ASR and our stakeholders didn't notice it. We put it back to wood. We relegate some of the ASRs into lower position and probably decide not to implement them and to implement these quality attributes in self. Now these no longer become non-ASRs. They become ASRs. So unless you can make them ASRs, they will always have a low priority in implementation. Now, if nothing works out and the client or the stakeholder is not willing to raise the priority, you'll simply let him know that if the ASR is to be satisfied, this particular module will be compromised and, well, we are not going to be able to satisfy this particular requirement. The third idea is generate and test. We have studied at some stage or the other a subject called testing of hypothesis. We have an initial hypothesis, often called by statisticians the null hypothesis. We assume that this is the hypothesis, this is the design that we will implement. And we assume that this design satisfies the requirements. Okay, this is an assumption. It's a hypothesis that here's a design selected by us and we assume that the design satisfies the requirements. Then we test, and we've got a number of methods which we have studied in the previous lectures as how to test whether the ASRs are being met by this design or not. There could be statistical processes, there could be a process of observation, processes of testing to see the quality attribute performance against the measurable goals that have been set. Thereafter, if satisfied, very good. We move on to the next step, to the next set of ASRs or to the next project. If not, we get back to generate another hypothesis, which again will be put to test. Now, this raises a number of questions. Where will the initial hypothesis come from? Who will test? When do we decide that we have got what we wanted? And how do we go around generating the next hypothesis? Okay. Initial hypotheses come from collaterals. Collaterals are material available to the project. They could be existing system, they could be frameworks that are to be deployed. They could be patterns and tactics. They could be a domain decomposition. They could be design checklists. These will give us an idea as to what could be a good design. We will find some designs which do not satisfy all the requirements. They do not even address some of the quality attribute requirements. However, out of the set, we try to look for a design which we think will be satisfactory. Our knowledge of patterns and tactics is going to be a major resource. Now, we have learned a number of techniques. We have learned that every quality scenario has a measurable response. So we go into the discussions, we understand the coordination model, we take the ASRs defined by virtue of the quality scenarios, and we verify whether the hypothesis, the design satisfies the quality attributes measured as we had decided right in the beginning. The end of it, we get a list of requirements in the form of either responsibilities or quality attributes. Against these, we know which have not been met by the design, either the quality requirements or the responsibility of the system. If the design has not met it, we get a list which is not met, and we decide that no, we have to go back, we have to have another hypothesis, think about it again. Now, how do you go around generating the next hypothesis? You try to put in some tactics. Maybe you tweak with the patterns, you make variations of the pattern. We know that through tactics, we can adjust the quality attribute satisfaction of a given pattern. So we try these out and we come out with a new design, which again we subject to test. We close the job. Either all the ASRs are satisfied, very good. We had architecturally significant requirements, measurable responses. We have satisfied them. We get done with it. Otherwise, if the budget is over, we simply take the best that's available, let the client know that, well, this is what is the best available so far, increase the budget, we continue our study, otherwise we accept it and we begin implementation. Alternatively, we simply let the customer know that, well, it's not possible with a reasonable effort. The combinations of ASRs asked for are not deliverable by a given system, pack it, and let's get back to reformulating the project. Now, we have something called attribute-driven design method. Let us understand what this method entails. It's basically a new name to old wine. It's an iterative method. At each stage, we choose the entire system or we choose part of the system. For the entire system or the part of the system, we decide on which are the ASRs that will be addressed. If it's a part of the system, which ASRs will be addressed? Is the entire system the entire ASR set? And we generate and test design for that part or for the entire system. Very often, the entire system may not address certain ASRs and they will be designated to certain subparts to handle. Architectural-driven design, attribute-driven design does not give you a design in one go. It's an approach. And in an iterative way, we put attributes into containers, into units, and each unit is asked to address those ASRs. So these containers and that's why we call it architecture. They interact and there's an information exchange between them, and put together they satisfy the ASRs for the project. So we come at the end of an attribute driven design method, we come out with a workable architecture early in the development process. We do not come out with an end product. We have attributes in mind, we focus on them, and we work towards the end. Now let's look at ADD, inputs and outputs. We start with three types of requirements: the functionals, the non-functionals, and constraints. Functional requirements is what the application is all about. The non-functional are quality attributes, what architecture is all about. And we have constraints, certain dictates by the stakeholders or the client saying that let's not discuss, this has to be done. Added to this, there will be continuous flow of input in our design process. Having been given these functional, quality and constraint requirements, there will be technical, social, legal, financial, political, you may call them interference, they may call them environmental factors. These will continually arrive to the architect. They will not come at one stage. They will come a little further down in the project. An architect very often, because of his experience, has got to anticipate them. He's got to understand that this is the environment in which I work. And with this in mind, he goes about the attribute-driven design. And the net result of this attribute-driven design is a set of responsibilities, types of interactions between components, a type of information flow, which could be shown under various views. We have looked up views in the past, we look at views in future. These are methods of presenting an architecture. So an architecture gets presented for implementation. Let's look at the steps that we follow in the attribute-driven design. First, we choose an element of the system to design. It could be the whole system, it could be a subsystem, it could be a sub-subsystem, it could be a module. And we identify the ASRs that are to be addressed by this element. We look for a design solution to fit that element. And then we note down what are the requirements which are yet to be implemented at the system level. And having done that, we select the input for the next iteration. And we continue with this until all the ASRs have been met. Let us go step by step. How do we choose an element? In a greenfield design where there are no constraints at all, it is the whole system. You look at the whole system, and if you can do a mumbo jumbo and come out with a design solution for the entire thing, very good. For legacy designs, you may have an element which is something to be added to the design. Well, we accept the legacy as it is, we don't want to change it, but we want to give it better security, better response, better interoperability. So these type of requirements will be there. So you will be looking at elements. So we number the elements and we iterate from up, down one channel, or we go sideways. The whole idea is you start with the whole system and gradually get more and more fine-grained in your approach. You either go breadth first, you may have a number of sub-items, look up all the sub-items one by one, and then you go deep within each module. So we could go breadth first, look up each module which put together forms the entire system, and then go to the next level, the next level. Alternatively, sometimes there's a new technology. There could be a concentration on a particular area where if there's a team that has got to be kept busy, then you go deep down vertically. You mine right down into one element, complete it, and having completed, you may have completed your project. Or then you shift out to other areas. So these two approaches any of them can be taken. Now, when you take up a particular element, it could be the whole system, it could be an individual system. If it's the entire system, we have already done the utility tree for the entire system. Take the most architecturally significant first. If you feel that some of these have got to be designated to a subcomponent, leave it out, address whatever else. But you take a holistic view to the system. But when you're working on individual components, on the decomposed tree, then you take up the ASRs which will be attended by that particular element and focus on them. You leave out the rest. We know very well that the rest will be taken care of by other elements. Then, having chosen the element, come out with a design solution. You list out the ASRs that apply to that element, develop a candidate solution inspired by patterns, inspired by tactics, taking the constraints into account. Use the design checklist for the quality attribute to see that we have been able to attend to what we wanted to. Whatever we decide at a particular step or for a particular module automatically becomes a constraint while working on other modules, because you've taken decisions here. It could be at the overall system level. You've taken certain decisions. These decisions become a constraint when you're working on ASRs for the subcomponents. So, if you find that some requirements have not been satisfied, which had to be satisfied at that module level, you can backtrack. What has not been satisfied should be basically functional responsibilities, constraints of the parents, or quality attribute requirements which are not to be met here. What are not satisfied, they have to be listed out. And then, having listed them out, you've got to assign them elsewhere. And you can create containers with similar requirements. If you can contain containers, then that container becomes a submodule to be worked on. If you find that something is getting very complicated, it cannot be handled under one unit, break it up. That is a pretext for breaking. That's an architectural decision. And make sure that when you break it up, you take care of low coupling, high cohesion. This is basic design strategies. And having split it up, each of the submodules may focus on a particular ASR. For each quality attribute, a responsibility and constraint. These are what we work for. We have responsibilities, there are constraints, there are quality attribute requirement. If it has been satisfied, then we need not bother about it. If a quality attribute requirement has not been satisfied, you will either delegate it to a child or you split it among various models. If it cannot be satisfied, we either weaken the requirement or we declare that it cannot be met. Let us take a relook at constraints. Anything given by the client, we call it a constraint. Why? Because the client has already put in due consideration and come to a conclusion where he does not wish to involve you in the decision making. He has decided that RDBMS is the best solution for him. So, well, that's a constraint. Similarly, once it comes to your architecture, any decisions that you have taken and you have satisfied quality attributes, they become constraints. There are some decisions you may have delegated to child elements. Well, if you're delegated to child elements, as far as this element is concerned, you treat it as a constraint. Don't break your head about it. If you split it into two units, again, if one of the two split is not the unit you're looking at, it becomes a constraint. And then, if you have taken a decision that certain things cannot be satisfied, it is not satisfiable, you've got it cleared with everybody involved, you put it down as a constraint and we don't try to look at it. Now, at the end of it, the fifth step is repeat step 1 to 4. At the end of 3 steps, each child element will have associated with it functional responsibilities, quality attributes, constraints. Now, in this process, we keep finding out whether we have completed the complete set of ASRs or not. If not, we are going back. If we find that at any stage we can afford to terminate, it is either because all the requirements have been satisfied, or you have reached a stage in the architecture where the architect feels that the implementation team is capable of taking on from here. They've understood the spirit of the architecture, and I do not need to detail it further. They've been working together long enough, and they have had similar experiences. More detail is not required. Or there was a contractual requirement. The stakeholders had indicated that you've got to achieve so and so. That has been achieved. You may be able to do better, but you don't need to. Your contractual requirements. Or your project budget is expired. Well, this is what you're going to afford to spend. Nothing better than this is possible. You let the client know that either we relook at the project or this is the best that can be done. In summary, let us look at what we have done. We have determined ASRs. We have been generating designs. We have been testing one of the elements. We have been trying to decompose, and we've been trying to satisfy the ASRs. And all this we do until we are either satisfied or we surrender. Now, this in nutshell is what we mean by attribute-driven design. Thank you.